so can you... Okay, shall I start? So, good afternoon everybody. In this lesson we will... Okay, so good afternoon everybody again. In this lesson we will address ICP on a manifold in 3D. So the statement of the problem is the following. Given a set of points in the word frame and a set of measurements in the robot frame, assuming that the correspondences are roughly known, we will come back on this later, then we want to find a transform that minimizes the distance between the corresponding points when they are expressed in the same reference frame. So we want to find the relative transform that allows to minimize the distance between corresponding points expressed in the same reference frame. Such a transform will either be the pose of the word with respect to the robot or the pose of the robot with respect to the word. However, as the calculations are easier in that way, then we will consider to estimate the pose of the word with respect to the robot. In this slide we have a summary of the least squares algorithm. In particular, you see that for each measurement the error is computed and the associated Jacobian, that is the derivative of the error with respect to delta x, and they are used, weighted by the covariance matrix of the measurement, to build the matrices H and B. The matrices H and B are the coefficients of the linear system H delta x equal minus B, which we solve to obtain the perturbation to apply through the box plus operator to the current estimate of the state to update it. Notice that we have a box minus here and a box plus here inside the expression of the error, and this is because both the measurement and the state can be elements of a manifold, respectively of the measurement and of the state manifold. As always, the methodology is the following. You will have to qualify the domain of the state space, which in this case will be SE3, a Euclidean parameterization that is consistent with the domain, that in this case will be R6, and the box plus operator, as you have already seen in the 2D case. Then we have the measurement space, and again we need to qualify the domain, define a Euclidean parameterization and a box minus, as the box minus is needed, for example, in the expression of the error. In particular, we need to identify also the prediction function, as we will see. So in this case, the state is an element of SE3. In the Euclidean parameterization is a vector belonging to R6. In particular, we have the first three elements which are related to the translation and the last three to the rotation. As a definition of the box plus, we use the vector to transform function that you have already seen in the 2D case. And in particular, it brings from a 6-dimensional vector to a homogeneous transformation matrix where the rotation is given by R delta alpha and the translation is given by delta t. You can easily verify that the product of a vector to transform delta x by x is given by this expression. As far as the measurement is concerned, we need to express a point in the word frame, pi, to a point in the robot frame, and therefore we need to apply the homogeneous transformation x blocks plus delta x to pi. And this is why if you do the product of this x blocks plus delta x to pi, then you get this expression, where you can also read it simply by applying x to pi and then r delta alpha delta t, which is the v2t of delta x, to the obtained expression. Here pi prime I, p prime I is constant, and we will use this in the following. Here we see the error function, where being the measurements Euclidean, the box minus is a simple minus. Here we have the expression of the rotation matrix that is obtained by composing the rotations along the roll, pitch and yaw axis. You have already seen both the first and the second line, which is the derivative of the first one. Then the line at the bottom of the slide is just the derivative of each of these rotation matrices computed in 0. And it will be used in the following slide, where we have the expression of the Jacobian. In particular, it has the Jacobian has as many columns as the elements of delta x, which in this case is 6, and in particular we can think of it as 2 blocks matrix, where the first one is associated to delta t and the other one to delta alpha. And in particular, the first block is simply the identity matrix, while the second one is the skew-symmetric matrix in P prime I, which I have already said that is constant with respect to delta x, with a negative sign. You can easily obtain this by considering these expressions of R prime in alpha x equals 0, alpha y equals 0, and alpha z equals 0. Here you see two pieces of code. The first one is for the expression of v to tv, where you see that given the vector, in this case a 6-dimensional vector t, the transformation matrix v, the transformation matrix t, is obtained by considering the composition of the rotations in the x, y, and z axis, while as far as the translation is concerned, you just have to take the components of the vector v that are associated to the translation and put it in the first three element, fourth column of t. Then the error and Jacobian function, you have already seen it in other examples. In this case, the error is given by a simple Euclidean minus between the prediction of the measurement and the actual measurement. The prediction of the measurement is obtained by applying the transformation x that defines the pose of the word with respect to the robot. While the Jacobian matrix has two blocks, and then you recognize the identity block and the skew-symmetric matrix of the predicted measurement with a negative sign. Here you see the function that actually implements the ICP on manifold, and in particular you see that in the internal for loop you have the computation of the Jacobian and of the error by calling the function error and Jacobian that we have seen at the previous slide, while h and b are computed and updated for each of the measurements and then used to compute the perturbation in the external for loop, and then delta x is used to compute x. Now let us see what you have in your folder. In your folder that is called 23 ICP Optimization on a manifold, you have two scripts. One is called ICP 3D no manifold versus manifold, and the other is ICP 3D statistics, which we will now see a little bit more in detail. Here I have the ICP 3D no manifold versus manifold, which I am showing to give you the idea of what is the difference between using or not the manifold formulation. So here you see that first of all in this script we are constructing the measurements given a set of 100 random points and an ideal position of the word with respect to the robot. Actually it's the pose of the word with respect to the robot. Then we are computing the measurements by applying this x true to the word, to the point in the words. Now what is important in this script is that we have two kinds of test. We have the test with a good initial guess, that means with an x guess that is similar to the x true, and another one with a bad initial guess, and in both cases we have both the ICP with and without the manifold formulation. And by running here ICP 3D no manifold versus manifold, you will see that the script allows you to plot the error in each of these four cases. And I will now show that, as you can see, the fact of considering the manifold formulation is particularly relevant in case of a bad guess, while it's less important with a good guess, as we might expect. Here we also have the comparison between the good and the bad guess with and without manifold. You can do this by yourself, just as I did now. As I was already announcing, we have another script that you can use, and this one concerns the problem of outliers, which you have already been talking about, in particular referring to robust kernels. So here we see that we have a for loop. The construction of the data set is just the same as before. But after that, we have that inside this for loop, we are considering a certain percentage of outliers, respectively 0%. Outliers means wrong correspondences, 0%, 25%, 50 and 75%. And in each of these cases, we are computing the ICP on manifold with and without robust kernels. What does this mean? This means that inside the function that actually does the ICP, we have a few more lines here that define what to do in case the chi-square is bigger than a given threshold. In this case, we want to scale the error by a factor that is given by the square root of the kernel threshold divided by chi, so that the larger the chi, the smaller the weight that we are giving to that specific measurement. Notice that this is a simpler method than what you have seen already talking about robust kernels. Notice also that in case a measurement is not such that the chi is bigger than the threshold, then we are saying that we have encountered an inlier, and therefore we increase the number of inliers for that specific iteration. And you can run this one as well. And yes, this is called ICP 3D statistics, and now you will see what the difference is in terms of error between using or not the robust kernels. Indeed, here we have the case in which there are no outliers, so 100% inliers, 75% inliers, and 50% inliers, and correspondingly we have the error with and without robust kernels, and as you see, with robust kernels the situation is much better than without. So getting back to the slide, notice that you can and should change the value of noise sigma and comment this line to see what happens. To conclude, have a quick look at the slide. We have talked about outliers and what the effect of using robust kernels is. We have seen how robust kernels are in this case implemented in a very simple way. You have seen more sophisticated ones. And so in the end we have seen ICP in 3D on manifold. We have addressed the difference between using or not the manifold formulation, and we have seen how robust kernels help in having a better error here. Recall this. So as a conclusion, always remember to follow the methodology that we have been talking about, and try out the scripts that I showed you. Now, if there are any questions or something, just write in the chat. Just write in the chat. Okay, so now I will stop the screening and Giorgio will continue.
So, welcome to this second part of probabilistic robotics. So, what Barbara has shown you before was a small wrap-up of what we encountered so far regarding least squares for problems with a small dimension of the state space. In particular, we have seen in action the formulation on the manifold. So, like, this was a demonstration of what could happen when your state space is not Euclidean, and so, like, how can we adapt the formulation by locally mapping the perturbation into an Euclidean state space by using the manifolds, by using a local chart. And also was a demonstration of a very, very simplistic version of a robust kernel that actually, like, is even much simpler than those introduced during the lesson. I invite you to test one of the many robust kernel functions within the same algorithm and to experience on like the performance of the system by using the scripts that we provided you. Now, a standard question in the exam, a standard exercise, is that I assign you a registration problem on some weird domain when the measurements could be lines, where the transform could be not only a rotation and a translation, but also a scaling factor or the like, or also some other weird expression of a relative motion in the state. Okay, so the purpose of this second part of the lesson is to first present you an exercise that attempts to do the registration with similarities. And second, there will be a proposed exercise where we will play instead with the measurement domain. Now, this new problem is very similar to the previous one from a conceptual point of view, but in this case, the kind of transform changes. So, this is the problem. We have a known set of 3D points in the space. Let's call them Pi. Okay? Then, and this forms our reference, our basically known map, or the position of the satellites, if you want to think about it. Then we have a set of generic measurements. Let's say that in this case we observe these points, but we observe them with when they are subject to a scaling factor. That means that in our local view of the observed map, of the observed constellation of points, we will not be able to tell the scale. But if we would be scaling, making our measurement larger or smaller, basically by multiplying each point by a constant, then we would be able to register these two constellations of points, Pi and our measurements, one onto each other. So in this case, basically the transformation that we look for is a rotation, a translation, and the zoom factor, which we will call scale. Okay? So the game is the usual one. We have a set of points that we talk, that is our reference. We have a set of observed points that is our measurement. And we know the correspondence between each point, each measurement and each generating point. And what we want to do is to find the transform. Observe that here I drawn the axis smaller, right? Like when you do the registration, the axis become bigger, just to denote that we are also zooming the point set in order to achieve the maximum overlap. Okay, this is the problem that we are tackling. Okay, so our input set will be consisting of a set of elements of R3, but our domain, our state will be different, because this time we have one additional player into the degrees of freedom of my transform, which will be the scaling factor. Okay, so what we want to do now is to formulate a problem that to formulate a least square implementation of a solver for this kind of problem. Okay. It is also possible to resolve this problem by using linear relaxation. I just let you think about it and let you think about the D matrix, but right now we will go down for the manifold formulation. Now, the state. The very first thing that we need to qualify, following the methodology, is what is my state? Well, my state is a member of the group of similarities. Okay? Barbara, please follow the chat, because I will not be responsive, so you answer the chat, and then in the end, at the end of this batch, there will be a proposed exercise, and we will have a question session in Zoom. So the state is a rotation, a translation, and a scaling factor. If you recall, in a homogeneous transform, we used to put in a homogeneous transform matrix, we used to put a 1 here in the last element. In this case, we put an S to denote the scale. Okay? You might observe that having mapped this domain of rotation, translation, and scale, this is the scaling factor, into matrices, allows us to compose them exactly as if they were regular transformation matrices. Because if we would be inverting this, we would be finding something that here has 1 over S, right? And then the game becomes consistent. Okay, so the similarities form a group similar to the special Euclidean group like SE2, SE3, SEN, and so on. Okay, so that they form a group means that they support an identity element, and they support the inverse, and they support a multiplication. Okay, which allows us to build the chains of similarities in general. Exactly as in the same way as you do when you express the kinematics of a robot, where you have a chain of transformation matrices. Similarly, you could have a chain of similarities. Sim3 is this group. Okay, now, this is a parameterization for the similarity, but I invite you to think that there's no point in the algorithm where we rely on this particular definition of the state a capital X, because this is for us a data structure. No one prevents us, for instance, to representing a similarity by using here, instead of a rotation matrix, a unit quaternion. In this case, our similarity will be constituted by a data structure consisting of 3 elements. One is a unit quaternion, one is a 3D vector denoting the translation, and one is a scalar denoting the scale. Okay. Clearly, if the scaling is equal to 1, then I do not have any zooming or unzooming effect. If the scaling is smaller than 1, then my element will be, the point multiplied by the similarity will be shrunk. If S is bigger than 1, then it will be zoomed. Okay. Now, having said so about my choice of the representation for X, note that here I have many more free parameters than what are the minimal parameters of my domain, because in this case I have 7, but here I have basically 9, 12, 13 13 parameters, not 3. Okay. Then once this comes, having defined this parameterization for the capital X, for the generic state, I have to define, following the methodology, a parameterization for the perturbation vector. I recall you that the perturbation vector should be such that if the perturbation vector is 0 and it is applied to one element of the manifold, then through the box plus operator, so if this is 0, then this operation here has to return me X, right? So if this is a 0 perturbation, then I don't have to move from where I am. Okay. Now there is something that a natural choice that someone might think about the representation of the perturbation vector would be extending the perturbation vector of SE3 by adding one single element, which is this S over here, to it. So we would have the translation part, the rotation part consisting of triangles, and here we would have S. But then we observe that if S is equal to 0, then basically this means that you collapse anything that you have in your transformation to 0. Like, that's not the identity element. If I here at the last point of my perturbation vector, I would put this S over here. Well, when I go back, when I construct a similarity out of this object, here I would have a 0, right? But we know that the identity element of a similarity would be the identity matrix, which has an identity in the R and one in S, because it should be an identity. So there's something odd over here. I can't just put S, this same element, over here. I will put an element that I call delta S, and then I have to invent a function such that when this object here is 1, because it is 1 only when X is an identity, then this S here is 0, right? And a function that is a continuous function that is 1 when that is 0 when its argument is 1 comes to be quite handily the logarithm. So in my mapping, I choose that this delta S here represents basically the logarithm of the scaling. This is a general trick often used when operating on manifolds. So if you have an element which has to be identity is 1, then you set it. Then you map it onto the chart by using the logarithm, because you know that then in the chart this will be 0. Okay, and then similar to what I have done for the SE2, SE3 and SE2 groups, I could invent a function that blows up a perturbation vector like that to an element of the similarity group like that. So that allows me to go from a 7-dimensional vector, Y7, because in the similarity you have 7 degrees of freedom, that blows up from a perturbation vector, construct me an element, a matrix X, that I can then multiply because they form a group. Let's call this operator V2S, no? So vector to similarity. V2S of delta X is straightforwardly, and this is for us, we could straightforwardly define it as, okay, you take the delta alpha part of the vector and you construct this rotation matrix. You take the translational part and you construct the translation vector, and then you take the scale that here was just the logarithm of S, and you invert the operation just by applying the exponent. You might observe that if I give if delta X is 0, this V2S, this similarity returned by V2S, will be the identity, because if the three angles are 0, then the rotation matrix will be the identity. If the three translation components are 0, then this block here will be 0. And if this object is here is 0, then the exponent of 0 makes 1. And so I am back to have an identity. That that in the end will result in the fact that if I multiply the similarity constructed by this object over here to an element, then I stay where the element is, because this is this will be the identity when delta x is equal to 0. Hope this is clear. The formulation of the similarities. Okay. If you have questions, please write them down. Then this is the first part. So the first part consisted in qualifying the state. And already, just it's only a thinking exercise. Like you have to think, to consider two standing points. What is the real domain that I'm approaching, and that typically you figure out just by a careful reading of the text. How many degrees of freedom do I have in this domain? And this will give you the answer on how large, what is the dimension of the perturbation vector. And then you might think on how to apply a perturbation to the domain in a way that when you define the perturbation, that the zero perturbation leaves you at the same point of the domain where you started. So the perturbation vector 0, when applied to an element of the domain, has to return you the element of the domain. And you can manipulate this part. There are standard ways of doing so. I will also put a link on the web on a paper that describes many of these parameterizations, but this is just for completeness. What is important for me that you feel is like what has a parameterization and a definition of box plus, what conditions should it obey so that it is a valid one. Okay, now this is my description of the state. I'm done with the state. Then I can look at the measurements. Okay, the measurements in this case, it's quite straightforward. They are just points in R3, only that they are related to the original points through a scaling. And then the question is, okay, assuming that I give you a scaling matrix like the one that I've subministered you before, how would you give me this point after the scaling? Well, the answer would be straightforward. You take the point, you apply a rotation, you apply a translation which is encoded in X, and then at the end you apply the scaling. If the scaling is equal to 1, clearly this is degenerates to the regular transformation of a point. Okay? And I have defined in this very same way the measurement that I should observe if the word with respect to the robot was in the similarity X. Okay? Okay. Then we need at this point to proceed, we have to add the box plus here and do our calculations just by exploding the definition of the box plus. Okay? So the box plus would like to derive this equation. You just go one slide back and then you do the calculations by expanding the product of this matrix here times this matrix here, and then applying, and this will return you x box plus delta x, and then by applying this definition for the scaling of the point. Well, operationally we could simply observe that assuming that this p prime with I is the point that I observe by applying the similarity, the point pi that I observe by applying the similarity encoded in X, then if I take this new point that I call p prime with I, and that is here, and then I apply the perturbation similarity delta x that is coming from the V to S, I just have to take the original point p prime with I, rotate it rotated of the rotation matrix encoded in the delta alpha, because delta x is a perturbation, so I have to recover a rotation matrix from the components of the perturbation. This is the point that has the same meaning of before, just like that it's subject to a scaling, and then I apply a translation. Once I've done that, to all these resulting objects, I have to apply the perturbation of the scaling. But I know that the scaling inside the perturbation vector is represented through its logarithm, and so in order to recover the effective magnitude of the scaling, I have to apply the exponent. Okay? Then, once again, observing that this component here is denoted by p prime with I, and by reasoning on the fact that when we will have to calculate the error function out of this, we only have to derive with respect to delta x, we could absorb all the components that depend on x, that are r and t, into an element that we call p prime with I, which is just a prediction. Okay? And we can then, this will finally lead us to this final formulation over here, where we have p prime with I that substitutes this part. Okay, and this will be in the end our final prediction function for this problem. This is a prediction function for the similarity that calculates the expected points, assuming that I know the rotation, the translation, and the scaling of my system. Okay. At the perturbations. Now I have the prediction function. The next step, I look into the menu, will be to calculate the error and the Jacobian, and then I start having fun. Luckily, in this case, I observe that the error, the domains of the measurements are not on a manifold, and then I breathe a bit. And then, because I know that in this case I will not have to deal with the box minus operator, and I start writing down my error function, right? Like, which will be the prediction at the perturbation minus the measurement. Instead of box minus the measurement, I just write down what I've written in the previous slide. I expand this prediction at the perturbations, and then I start computing my derivatives. Now, the derivatives in this case will be how large will the derivatives will be. Now I will be waiting, and this is also a way for me to measure the latency of YouTube. How big will be the Jacobian? Question. I will not proceed in the lesson if I don't receive at least one answer. Or I will wait for 5 minutes until proceeding. How big is J? Dimensions. Please answer. How big is J? Hold on. No answer. Yes. Excellent. Exactly. Error dim times perturbation dim. Okay. So like when in the exam you have this question, and if you make it wrong, I get sad. Why? Okay. 3 by 7 I understand. Lorenzo, you have to explain me why 4 by 7. But if my measurement is big 3. But then we will talk at the question time. The Jacobian is always the dimension of the error times the dimension of the perturbation. Okay, because it's a derivative, and derivative with respect to this object, and the domain is the domain of the error function. So it's 7 element, right? Now it will be a 7 element which will be consisting of a 3 by 3 block, and which is the derivative of this function here with respect to the translation, evaluated in 0. the derivative of this function, which is with respect to the rotation part, and the derivative of this function with respect to the scaling part. This is a 3 by 1 vector that is added to the previous one. This is surprisingly and spectacularly similar to the Jacobian of ICP at the manifold, right? And this is like kind of interesting because we can reuse part of what we know. Now, remember that we have to calculate this derivative and evaluate it in zero. Okay? Now, the first part of this derivative will be the derivative with respect to delta t, evaluating all objects in zero. So the derivative of this object with respect to delta t will be exp delta s times delta t, derived with respect to delta t. Given that delta s is a constant evaluated in zero, exp of 0 is 1, so this object here will be just the derivative of delta t with respect to delta t. And I put happily an identity. The derivative of this function here with respect to delta alpha by setting delta s and delta t to 0 will be just the derivative of a rotation matrix in alpha multiplied by a point, which we have seen in the previous slide, that becomes minus a skew-symmetric matrix of the multiplied point. And the last one, which is the derivative of this function with respect to delta x, will be, we freeze this object over here by setting delta alpha and delta t to 0, which will become just p prime with I, multiplied by the exponent of delta x. The derivative of this will become, again, the exponent of delta x multiplied by p prime with I, then evaluated in 0 becomes 1 multiplied by p prime with I. Hence, the last column will be consisting of p prime with I. And then we are done. We have also our Jacobian. Do we have everything? Yes, it seems so. We have everything, and we can proceed with the synthesis of our program, of our algorithm. Okay? And we go. Oops, did I move my image on OBS? Yes. And here we go. The very first thing that we do is to write down the function v2s that returns, construct a similarity out of a perturbation vector. We will also be using the function v2t that we have written before, because we know that the first six components of the perturbation vector map into the part of the transformation matrix that are the same as the one reconstructed from a perturbation vector for SE3. So the very first thing that we do is that we put into the R and the T part the rotation matrix and the translation vector extracted respectively by the last three and by the first three components of our input vector. And the final part will be, consistently with the slide, to calculate the exponent, this is the S, of the last component of V. And this gives us a similarity, right? That is a group, and so we can multiply happily with all other similarities. Okay? And then we have to write the famous error and Jacobian functions just by copying the code, and this is a one-to-one translation of the code of the math that we have seen in the previous slides. We extract the translation vector, we extract the rotation matrix, we extract the scaling factor, we calculate the prediction, so-called z hat, which is equal to S times R times P plus T. We calculate the error as the measurement minus the prediction. We calculate the Jacobian, and we assemble the Jacobian based on the rules that we have seen one slide ago, which is here, right? First will be the identity, then there will be the minus skew-symmetric matrix, and then the last one will be P prime with I, which is our prediction. So identity minus skew-symmetric matrix and our prediction. Okay. The algorithm, I think this should be So this is dimension 7, the correct code, this is a mistake. All these objects here should have dimension 7, but this is just because I copied the wrong file on the slides, but we will see the code running correctly. And then, therefore, the last slide of this pack is testing. Then I will show you this program running, and then I will introduce the exercise that we're gonna do in Zoom. Okay, I invite you to pull the repository of the fresh version of the repository. The slides, I've corrected them, but they are not yet up. They will be up in a few minutes when I will switch on Zoom. Anyway, no, this is the exercise. I'm supposed to run the program now. B. Here you have two folders, one which is called norm and one which is called similarities. Norm is the exercise, similarities is the demonstrator of what I've explained you now. Let's see if it works. I'm gonna change editor. Without too much fantasy, I always called it ICP 3D test. So in ICP 3D.m you find the functions that I was commenting before. You have the cool error and Jacobian, and maybe there is some sort of settings, preferences, font and colors, but I don't know in these plugins, but I don't know in this program, in this editor, how to enable the highlighting, but we will live without. This is the ICP function, and coherently, or the registration function that with an abuse I always call do ICP. The pattern is always the same, only that the system, linear system now is 7 by 7 because my perturbation vector has a dimension 7. Okay, and then we're gonna see, believing that it's Emacs, regarding the generation of the data, that in the next exercise you will have to do, because I realize that it's also important to challenge you in constructing the problem you will be working on later on, so that you become more autonomous. We generate 100 points, we set an inverse scaling of 0.5, then we generate a transform, which we call this, which has 7 components. Clearly the last component is a log, right? Like is the log of the inverse scaling. Then we compute the measurements exactly as in the same way that we were doing with ICP. We calculate a set of the measurement. Okay, we calculate. These are the points in the word, and then we have to construct our points mapped into the reference frame. And so we basically multiply our similarity by the points that we blasted, that we increased with the homogeneous transform, because we add a 1 to the points in order to support the homogeneous operation, which means that XYZ1 will be one of our points. Okay. Then we add, potentially might or not add the noise. What happens if you remove this? Probably you will slower the convergence based on the amount of noise that you add to your estimated points. In this case, we also use a damping. A damping factor is an identity added equal to the damped pseudo-inverse that you have seen in robotics, just like to get the system converging a little bit slower and keeping it away from rank deficient conditions. We run our program with directly with a bad initial guess, and we plot the results. Like the pattern is always the same, and then we will see the evolution of the chi-square that we expect to be decreasing over time. Now let's hope that this object works. So like if I start the ICP 3D test, then this stuff should be working. Now is machining. Okay. Then in the end, I have found a similarity. This was the similarity that I had as input, and this is the similarity that I was looking for, the ground truth, and this is the result that you might see that is quite decent because these two are the same. And so how do you figure this out? This is the evolution of the chi-square. Okay? And we start from this error and we finish from this error. The message of this demonstration and this lesson is like that with little x you could like really solve uneasy problems with this mechanism once you learn the mechanic. Please, the mechanic or the way of reasoning is straightforward, and there are 2 or 3 things that I would love you to remember at the end of this course and probably throughout your career, like how to do certain things, how to formulate a least square problem that serves actually the purpose, and how to use this set of tools like filtering and so on, and a little bit of sensibility on what could go wrong and which tools to use for solving which problem. But this will come in a while. Okay? I'm talking at the end of this course, not for the exam. For the exam I expect much more, but like, you know, we all tend to forget things after we don't use them for a while. I would like that this stuff that I mentioned stays alive for a bit, because I think it might be useful to you in your career and your working life. You'll become the magician that can solve problems that many of other people are struggling with. Okay, so this don't say. So we come back to the slides, and now I'm gonna present. Barbara, could you set up the Meet and send the email, the Zoom, and send the email to the folks? And meanwhile, I present the exercise, and then we will switch to Zoom to support our folks in doing the exercise. Okay? So the exercise is the following. We have a model, right? Our model is this set of, so now this concludes the part, the lesson part on the similarity, and now I'm gonna propose you an exercise that I would like you to do now, like while we are assisting you on Zoom. Okay? The code for this exercise is in the repo under the folder norm. Given that I made a mistake, you also have the solution, but please don't look at the solution, because otherwise the meaning of the exercise evaporates. Try to work directly on the non-solution folder. No? Now, yeah, this is my neighbor that loves to move chairs while we have lesson. I think he's watching us on YouTube. We have a model consisting of n points in the 3D space. Our state is thus the position of the word with respect to the robot, like this is what we want to estimate. So we are within the setting of a registration problem. But our measurements in this case, well, they are not just points, they are points with a constraint. So like basically what we observe is a set of direction vectors. So assuming that my robot sits at a certain location and observes a point, well, then this observation is not the relative position of the point as seen by the robot, but this observation is just the direction vector of such an observation. So basically it's what we were observing in regular ICP, but just that it is a normalized vector. Okay? So we just observe directions. This is a little bit equivalent to this bearing only registration that we have done in SE2, right? Only that we are in 3D, right? And this is actually a very important class of problems because it's characterizing all sort of generic camera problems, because the camera observes only the direction of an object, but it doesn't observe the distance if you see a point, right? So like if we're talking about normalized vectors on the unit sphere as measurements, then we are talking about these direction vectors. So what you observe is a vector z, z of h of a, remove the delta x, this is a mistake of me. We have point z, a measurement, which is parameterized maybe by x, y, z, but there is a constraint on this point. Z should belong, the norm of z, so x squared plus y squared plus z squared, should be equal to 1, right? That means that the point has to lie on a sphere, and this domain here of points on the that have norm 1 is called the domain, is a manifold, is the manifold S2 of the sphere. Okay? Now, please forget this box plus delta x that is left from a copy and paste error. Basically, my prediction function for hi of x without box plus delta x will be just the old prediction function of the ICP with the normalization. So I have to take the norm of this vector and divide it by the vector itself. Okay. Now to carry on this exercise, I suggest you to use a simple trick for now, which is don't carry on the box minus operator, although you could, right? Just consider the measurement as an element of R3, okay? So like don't use the box minus operator, just operate on a 3D unit vector, okay? This is my suggestion. And then we can also apply the manifold formulation that will work better in general for the error, okay? Just to show you the code, what we have to do, and then we go on Zoom. Oops, I don't see the. Excellent. I show you what you have to do. Close Octave Evil. There is a fantastic folder which is called the norm. And inside there is a folder which is called exercise that you have to look at, and a folder called solution that you don't have to look at. Not yet. There is a program which is called the test norm registration.n. What I expect you to do here, sorry, but I have to use this editor because anyone else, any other, I'm not able to. So we generate a set of points, which will be our reference point. We generate an Euclidean pose. That could be this, for instance. And we, out of this Euclidean pose, like this is a perturbation vector, then we bloat it up to a transformation matrix. And then out of this measurement vector, we would like to generate a matrix of measurement, which is conformant with this matrix here. Well, this matrix will be obtained by transforming each of these points according to the ground truth pose, but then after that we will also have to normalize these vectors, because this is the new problem that we are addressing here, right? Then here we put a little bit of errors in the ICP loop, because this might help you debugging. So like, yes, it's very helpful. And of course, the meat of the exercise is in the error and Jacobian soup. And then this time I put you in cold water. meaning that you have to do everything by yourself. Okay? I mean, I originally would start on thinking a little bit about the structure of ICP, or just like proceeding by deriving the error function, remembering the chain rule, right? Because the normalized function is a function that could be differentiated, right? And so like one could use the chain rule to assemble a Jacobian, which is basically obtained by the Jacobian of ICP multiplied by the Jacobian of the normalization. All right. Once you have done that, you will have something that presumably works. Let's see. Test norm registration is a program itself. Yes. And then I will be going to the solution. So, solution. Registration. Okay, well, this is, I'm completely unable to do plots in Octave, so articulated plots, so I'm happy when I see that the chi-square goes down, and then I assume that if the error function is done well, then everything would work. Okay? So like what I expect you to do is first to generate the data, then verify by putting to 0 the error, verify that the error function that you write is consistent. Of course, you might also want to look at the data and to figure out whether the vector that you generate have the measurement that you generate have a unit norm, and then craft this system, spotting the million of errors that I joyously distributed around, that are more or less they cover 70% of the errors that I'm able to do when I write such a small program. Now, let's see each other on Zoom. I will log out, log in, and be back in 3 minutes. You can start with the exercise. Me to drink. Okay? Have fun, enjoy, and see you in 5 or 3, whatever, soon. Ciao, ciao.